This conference will now be recorded.
Hello everyone. We will start with a problem, and after that the topics that we'll discuss is tendency to form complex for D block elements, then catalytic properties, alloy formation tendency, interstitial compound formation tendency, formation of oxide and oxoanions, and related problems. Here the problem is total 4 different types of behaviors present in options A, B, C, D. We have to find which of the following arrangement does not represent correct order of the property that is stated against it. So 4 different properties are mentioned. The first one is paramagnetic behavior. Second one is ionic size, then stability in aqueous solution, and number of oxidation state. Okay. So the first one, we have some ions, all are in +2 oxidation state, V2 plus, chromium 2 plus, Mn2 plus, Fe2 plus. Now V2 plus, that is paramagnetic behavior maximum for Fe2 plus according to this order. Now it means that maximum number of unpaired electron should be present for Fe2 plus. So we have to basically find out for each of these 4 species how many number of unpaired electrons are there. Because higher is the number of unpaired electron, higher will be the paramagnetic behavior. So for vanadium, when it is neutral, it has configuration 3d3 4s2. So when it is V2 plus, there will be total 3 unpaired electron. Chromium, it has configuration when it is neutral 3d5 4s2. So when it is chromium 2 plus, there will be total 4 unpaired electron. For Mn, when it is neutral 3d5 4s2. So for Mn2 plus, it will be 5 unpaired electron, and Fe2 plus, Fe when neutral it is 3d6 4s2. So when it is Fe2 plus, there will be total how many unpaired electron? Now it is not that 6 unpaired electron, because maximum capacity it is 5 only. So the 6th electron it will make a pair. So now number of unpaired electrons are only 4. But here it is mentioned that maximum paramagnetic behavior is for iron, but that is not true. Actual order should be Mn should come before Fe, then only it is correct. So the first option is basically not correct. So if you have done this correctly, even and if we are lacking time, even without considering other 3, you can choose this as the correct option. But you will also see the other ones. Ni2 plus, CO2 plus, Fe2 plus, Mn2. Ionic size. Now, as we are moving from left to right, what will be the elements? The first element will be Mn. After Mn, next one is iron, then cobalt, and then nickel. That means when you are moving from left to right, size is decreasing. So maximum size that should be for Mn, then Fe, then CO, and Ni. And it is matching with this order. So this second option, it is correct, true. This is false. Then stability in aqueous solution. Now stability in aqueous solution, that is actually related to reduction potential value. And in last class also we have seen reduction potential is also dependent on so many other factors. So directly we cannot predict what will be the stability order, whether it is correct or not. If you really want to know the stability order, basically we should know the reduction potential value for each system, because then only we can say whether the stability orders are correct or not. So see here values are given. For the first option, this we have already done. Then order of paramagnetic behavior, this is the correct order, which is not present here. So that is why this is the correct option, because we have to find out which does not represent correct order. Now the second one, that is also correct, decrease from left to right. Now come to the third one. Here all these systems are M3 plus 2 plus system. Okay, that means when M3 plus is accepting 1 electron, it is converted to M2 plus. Okay, now is this 3 plus oxidation state, it will be stable only when the metal can easily donate electron. That is metal 3 plus that will donate electron, and sorry, metal 2 plus that will donate electron, and it will be converted to M3 plus. So electron donating tendency of M2 plus, if it is very high, then the stability of M3 plus that will also be very high. And from the reduction potential values, we can easily understand that which one is basically having maximum reducing tendency. Here, higher is the negative value, higher will be the reducing tendency. So as negative value, it is 0.41 for chromium 2 plus 3 plus system. That means chromium 2 plus, it can easily donate electron and it can easily convert it to Cr3 plus. But this process is compared to chromium for iron, now the value is higher. That means compared to chromium, now Fe3 plus, it will have reduced tendency. And cobalt 2 plus 3 plus system, it is very high value, 1.97. That means it will prefer to stay in CO2 plus state, not CO3 plus. That means CO3 plus is not very stable. And what about scandium 3 plus? Scandium 3 plus, just see what is the electronic configuration for scandium. It is 3d14s2. That means when it is 3 plus oxidation state, basically it is 0. Okay. And Sc3 plus, it is very stable because it is having 3d0 configuration. Okay. So it doesn't show class 2 oxidation state in aqueous state. So that is why this is very stable. So maximum stable will be Sc3 plus because it's 3d0 system. Next one will be chromium, then iron, then cobalt. And it is completely matching with the order that is given in the question. So that is why it is correct. And what about the last one? Number of oxidation state. We know when we are moving from left to right. Here we have these 4 elements. So scandium comes first, after that titanium, that is we are gradually moving towards right hand side direction. After titanium there is actually vanadium, but here we do not have vanadium, so I am writing chromium and then manganese. Now maximum oxidation state, remember, that is found in the middle zone, and that is actually for Mn, +7 oxidation state, which is maximum. So as we are moving towards this side, number of oxidation state will increase. So that is why this order is completely correct and this order is also fine. So which order is not correct? It is the first option, option A. So in this problem, is there any doubt? Next topic is tendency to form complex. Now complex formation tendency you will hardly see in case of S block and P block elements, but this is very common in case of D block elements. Okay, but we have to know what is the reason behind it. Why transition elements show tendency to form large number of complexes? Transition elements are good at forming complexes unlike S and P block. Though in S block you can find some complexes, but that is very few examples. Compared to D block, that is nothing. Now here the reason that transition elements, they show a very large variety of complexes. The reason is they have small, highly charged ions. Now compared to S block, after S block we have D block in the periodic table, and gradually the size is decreased. That means size is small and high charge. We know that for D block elements, different types of high oxidation states are possible, +6, +7, that are not possible for S block. S block maximum oxidation state you can find +1 or +2, right? But for D you can find very high oxidation state. So highly charged ions and size is very small. That means charge density. Charge density means charge divided by volume. Now charge is very high and size is very small. Now size small means volume is also small. So here the denominator is very small but numerator is large. That means charge density is high. So that is why their complex formation tendency is very good. And they also have vacant low energy orbitals which can accept lone pair of electrons donated by ligands. Because when this type of complex are formed where ammonia and CN, all these are basically ligands. Now they will donate their electron density towards the vacant orbital. So both the electrons will be donated by the ligand towards metal. So it is like this. It is actually coordinate bond. It is not that metal is also giving electron, ligand is also giving electron, then the bond is formed. No, it is not like that. If it is like that, then it will be covalent bond. But actually it is coordinate bond. Both the electrons are donated by ligand. Okay. Now, if ligands are donating electron, metal must have some vacant orbital so that it can accept those electrons. And for d block elements, those vacant low energy orbitals that is present. So complex formation tendency is high. Now here we have the picture of all the 5 different types of d orbital, and we know that we have already discussed it, that dz square and dx square y square, these two have some similarity. And what is the similarity? Here the lobes are on the axis. You see, the axes are directly moving through the lobes, but for the other 3, the lobes are in between the axes. So this is the difference. Now if you want to form sigma bond, that is actually head-on overlap. Suppose you have 2 p orbitals, so they will be overlap like this. And if it is suppose 2 dz square, then also as it is along the axis, sigma bond formation possible. So these two orbital, that is dz square and dx square y square, they are very suitable for sigma bond formation. And the other ones which are not along the lobes, they are suitable for pi bond formation. That means among these 5 d orbitals, some d orbitals are good for sigma bond, some are good for pi bond. So see here, these 2 orbitals, they are useful for sigma bond formation, and these 3, they are useful for pi bond formation. So both the type of bond formations are possible. Okay, so that is why when there is complex, maybe in some ligands, though these 2 ligands we are not going to detail, but suppose if there are some pi bond formation possible with the p orbital that is present in ligand, in that case pi bond formation is possible because metal has different types of d orbitals. Some are suitable for sigma bonding, some are suitable for pi. So as it has the capacity to form both kind of bonds, that is also another reason that it can form large number of complexes. Okay, here we have these 2 examples. Ammonia is neutral ligand, so that is why the 3+ charge that is present over metal, that is also present outside the coordination sphere. And for Fe2+, 6 cyano, that means 6 negative charge. Total positive charge 2+, that means 4 negative charge will be excess, and that is mentioned outside the coordination sphere. Okay. Now we have to know some idea about the crystal field splitting, though that is actually under different chapter, which is coordination complex, because the tendency to form complexes for d block elements, this is so important. There is different chapter for this. Okay, so this crystal field splitting will be discussed in detail, but if we want to understand that is why they forms so much variation of complexes, then we should have some primary idea about the crystal field splitting. So in this picture we have a cube. Okay, this is the central metal ion, or it may be any neutral metal, both are possible. So it may be metal 0 or some oxidation state. Now if you observe these black dots, black circles, they are having tetrahedral arrangement, right? But if you look at these gray balls, total 6 are there. Their arrangement is octahedral. Now if I am drawing, suppose there is x-axis like this, then y-axis and z-axis. Now see here in octahedral geometry, all the ligands, so these are basically ligands, total 6 ligands are there. Okay, all these are approaching along the axis, but when you are considering the black circles, they are actually for tetrahedral geometry. This is also ligand. So suppose these are L prime. L is for octahedral, L prime is for tetrahedral. Now the approach of the L prime, that is not along the axis, which is clear from this picture. Is there any doubt? The picture is clear. That is, both the geometry are given in the same picture so that we can understand the difference between tetrahedral geometry and octahedral geometry. In tetrahedral geometry, ligands are not approaching along the axis. So that is why in tetrahedral, crystal field splitting will be there, but this gap between E and T2. See, here we do not mention G. G is basically short form of Gerard, and that is possible only in symmetric complex. But tetrahedral complexes are not so symmetric, so that is why we do not mention the superscript G. We use T2 and E, not T2G or EG. Be very careful. But when it is octahedral, it is T2G and EG. Another difference is that when it is tetrahedral geometry, here T2 is having higher energy, E is having lower energy. But in case of octahedral, T2G lower, EG higher. But here the gap between this T2 and E and the gap between EG and T2G in case of octahedral, see, this distance is very high. Now here crystal field distance is high compared to these degenerate 5d orbitals. That is when metal ion is free. No ligands are approaching. So this is the energy under that condition. But when ligands are approaching, now there will be splitting because now all the d orbitals are no longer degenerate. Some d orbitals having higher energy, some d orbitals having lower energy. So in case of octahedral, these three orbitals are having lower energy because these orbitals, the lobes are not along the axis. But these two, the lobes are along the axis. So there will be direct interaction with the ligand when the ligands are approaching along the axis, and that is why their energy will be high. And these three having lower energy. But for tetrahedral, now the situation is different. Though it is true that ligands are not approaching at all along the axis, that is true. But if you basically you have to visualize it, otherwise there is no way to make you understand. That you have to just imagine and visualize in 3 dimensions that when ligands are approaching in tetrahedral geometry, that is the black spheres, okay, then these two orbitals are closer towards the ligands, but these two orbitals are not closer towards the ligand, but these three are closer. So that is why their energy are now high. But still, if there is any doubt in this picture and if it is not clear, then in the other chapter, which is coordination complex chapter, there this concept will be fully clear. We are not just trying to have some introductory idea, okay? And here this total energy, which is denoted by del O, and here it is denoted by del T, okay? Now compared to 0, this is 2/5 of del O and this is 3/5 of del O. But when it is tetrahedral geometry, now this gap is 3/5 of del T and this gap is 2/5 of del T. Now this crystal field splitting, that is affected by these 4 points. So why these 4 points are actually affecting crystal field splitting, we will see one by one. Crystal field splitting, that is what will be the gap between this higher energy orbital, lower energy orbital. This gap is dependent on these 4 factors. Now the first one is strength of the ligand. Suppose if the ligand is very strong field ligand, though strong field ligand, weak field ligand, that will be discussed in detail in another chapter, but just right now remember that there are 2 types of ligand: strong field ligand, weak field ligand. Now strong field ligand, when present, then interaction with the metals orbitals is very high, and as a result the gap between EG and T2G is very high. So when it is strong field ligand, the gap between EG T2G, that will be very high compared to weak field ligand. And how you will understand which ligand is strong field, which one is weak field? There is a specific chart for that, which is known as spectrochemical sensor. There it is completely mentioned, clearly mentioned, which ligands are strong field, which ligands are weak field. Type of complex. Type of complex means, is it tetrahedral or octahedral? So depending on that, different splitting are there, because you can see in this picture when it is octahedral the gap is very high, but when it is tetrahedral the gap between E and T2, that is very small. So this is the second point. The third point, size of the metal. Suppose the metal, that is the central metal, ion or atom. Ion is when it is carrying some positive charge. Atom, we will say when it is zero oxidation state. Now, if it is very small in size, then also interaction with the ligands, it will be good. So size of the metal is important. And finally, oxidation state. So same metal, suppose iron, it may have +2 oxidation state. Another possibility is it is +3 oxidation state. Now, when it is high oxidation state, it is not just for iron. I'm just taking this example arbitrarily. When it is 3+, basically it is more electron deficient. So interaction with the ligands, that will be now high. So higher is the oxidation state, higher will be the interaction with the ligand, and the splitting between Eg and T2G, that will also be very high. So these are the 4 points on which crystal field splitting is dependent. Okay. Any doubt? Should I repeat any part? Here we have a picture for different d electron system, D4, D5, D6, D7. So here we have not taken D1, D2, D3, then D8, D9. These systems we have not taken because this low spin, high spin concept, that is applicable only for this 4 system. Now what is low spin, high spin? Low spin means when the gap between Eg and T2G, this is Eg and T2G, when the gap between Eg and T2G, it is very high. As a result, what will happen? The electron will prefer to remain in T2G because if it wants to go towards Eg, it has to cross a very high, large distance. That is the gap between Eg and T2G is very high. So that is why the number 4th electron, after filling 3 electron, number 4th electron, now it is in T2G, it is not in Eg. But if the gap between these two, it is low, though from the picture it seems same gap, but actually it is high gap and low gap. If the gap is very small, now the 4th electron, so this is the 4th electron, it can easily be promoted to Eg. Okay, so for D4 system, 2 types of spin possible. Low spin is generally observed when it is strong field ligand, because when it is strong field ligand, the gap between Eg and T2G is very high, and the complex will prefer to form low spin complex. So it will, the configuration will be T2G4, but in the high spin, the configuration is T2G3 EG1, right? So this is the difference in electronic configuration. Now when it is 5, the 5th electron, now it is here, still it is not going to Eg because here some possibility to remain that is present. But in high spin, 5th electron, now it is promoted to Eg. So here the configuration is T2G5 Eg0, but this is T2G3 Eg2. Okay. Now for D6, T2G6, but this is T2G4 Eg2. And for D7, now see the 7th electron, it has to move to E because here capacity is no longer to hold one more electron, that is not present. But still here the configuration is T2G6 Eg1 and this is T2G5 Eg2. So see the difference in electronic configuration. But when it is D1, D2, D3, actually low spin, high spin, it is not possible because up to D3, all the electrons will be in T2G only. And when you are moving to D8, basically you will see whether it is strong field or weak field. That doesn't matter. It will always be same. So suppose if it is low spin, this is E, this is T2G. Now if it is D8, that means 6 electron will place here. So maximum capacity is reached. So the next 2 electron, that will be now in Eg. So this is basically T2G6 Eg2. But if D8 system you are considering for high spin, Now how we will place the electrons? 1, 1, 1. Then you will move to Eg. But the 6th electron now you have to mention here. 6, 7th electron, 8th electron. See, this is also T2G, Eg2. So both are actually same. There is no difference in electronic configuration. So that is why for D8, D9 and D1, D2, D3, low spin, high spin concept is not applicable. It is only possible for D4, D5, D6 and D7. Okay, any doubt? So complex for that is formation tendency is there, and we have already seen some of the examples of complex. So here we have how to, that is the picture from which you will be able to understand how to represent this. Here this is the metal which is transition metal, obviously d block metals. It is central atom, okay, and n number of ligands are present, and this number will be called as coordination number. So if there are total 4 ligands, coordination number is 4. If 6 ligands, coordination number is 6. Okay, and L is obviously ligand, and if the ligand is neutral, then the residual charge which is present outside the coordination sphere, that is also the charge of metal. But suppose the ligand is ionic in nature, some of the positive charge of metal will be reduced, and the excess negative charge or positive charge, depending on the complex, that will be mentioned outside the coordination sphere. So these complex compounds, they are special class of compounds in which metal atoms or ions, they are bound to number of anions or neutral molecules. So anionic ligand examples are Cn minus, Br minus, okay. But neutral ligand examples are NH3, that is ammonia, water, all these are neutral ligands. Both are possible. So metal ions or atoms, they are bound to a number of anions or neutral molecules with characteristic properties. Okay, because there is a specific geometry, tetrahedral arrangement or octahedral arrangement. So these two arrangements are most common. So that is why I am giving examples of these two. This is the old term that is used, but nowadays, that is modern terminology, these compounds are called coordination compounds. So in some books you may find it is mentioned as complex compounds, but better to use the term coordination compounds because here coordinate bond is present. That is the bond between metal and ligand. Suppose if it is Ml4 complex, so it will be like this: Ml 4L ligands in tetrahedral geometry. So all these bonds are coordinate bond. It is not covalent. So that is why we call it coordination compounds. Okay. We have a problem here. Transition metals have a strong tendency to form complex. Because of which reason? 4 statements are given. But what among these 4 statements, what are those statements which are actually responsible for the transition metals to form complex? The first reason given, smaller size of metals, variable oxidation state, high ionic charge, and availability of vacant D for bond formation. Now just try to recall previous slide. That is, I'm talking about this slide. Here the question is given why transition elements, they have a high tendency to show to form complex. Okay, so here see what are the reasons mentioned: small size, highly charged ions. Okay, then vacant low energy d orbital. So 3 reasons are already mentioned here. Now come to the question. The first reason, obviously it is correct, smaller size of the metal, which is basically responsible. And what is the reason behind it? That I have already discussed when I that slide I have completed. Okay, so smaller size, that is true reason. Variable oxidation state. Now this reason we have not mentioned. Variable oxidation state means we know that for D block elements there is so much variation in oxidation state, +2, +3, +5, +6. But these are not responsible for complex formation tendency. Variable oxidation state, it is actually the reason for the D block elements for which they show catalytic property. We will also discuss that later. But right now we are discussing complex formation tendency, but it has nothing to do with the variation in oxidation state. So this is not correct one. Now if 2 is not correct, 2 is present in option A only, so this cannot be the correct option. Then third point, high ionic charge. Now high ionic charge, that is also one of the reason, because when charge is very high and size is very small, then charge density is very high. And charge density high means strong tendency to form complex. So this is also a reason. So 1 and 3, these two are correct reason. And the last point, availability of vacant d orbitals, that is also the correct reason, because ligands are donating electrons to metals. So metals must have some vacant d orbitals, otherwise how it will accept electron from ligands. So correct option reasons are 1, 3 and 4. Okay. Transition metals form large number of complex compounds because of comparatively smaller size. Number 1 reason, high ionic charge. Second reason, this is number 1. Number 2, and availability of empty d orbital. This is number 3. Okay. So correct option 1, 3 and 4. But 2 is not correct. Okay. Now see catalytic property, and here you will be able to understand why variable oxidation state. This is actually the reason for catalytic properties. Many transition metals and their compounds, they have catalytic properties. Catalyst means this is a species which will take part in reaction, but after the reaction is complete, you can get it back intact and you can again use it for the next cycle. So that is the catalyst. It is used in very minute amount, but it helps in the reaction. Reaction rate will be high. So that is the property of catalyst. Now there is use of transition metals as catalyst, and also some of their compounds are used as catalyst. And mainly here some metals are mentioned. These metals are used as catalyst. Very common. That doesn't mean that other metals are not used as catalyst. That is not the thing, but these are most common. But what is the reason? The first reason, variable oxidation state, and this is the most important reason. Now when it is variable oxidation state, they can switch between the oxidation state. So suppose if I am saying that same metal, it can have oxidation state +2 and +3 also. Now when you are using metal in +2 oxidation state, that is when you are adding the catalyst, it is in +2 state. But after the intermediate is formed with the catalyst, that is now having 3+ state. Then again it is going back to 2+. So this type of switching between oxidation, different oxidation state, that is possible. And as it can show different oxidation states, so that is why it can switch between different oxidation states. But just take example of sodium. Sodium is having only one oxidation state, +1. There is no variation in oxidation state, and this is from S block. So as there is no variation, no question of switching between oxidation state. So here intermediate can be formed with other oxidation state of the metal, and again it can convert to the original state. Because after the reaction we know catalyst, there is no change in their chemical nature. So they form unstable intermediate compounds and provide a new path with lower activation energy. That is the main role of catalyst. Not just here, it is the common property of all the catalysts that it decreases the energy of activation, and that is why rate of the reaction increases. So these reaction intermediates readily decompose and it yields the actual product, and the metal catalyst is regenerated. Now we will take one example. Here the main reaction is this, and here the catalyst that is used Fe3+. Now if you look at this single step, you will not be able to understand what is the role of Fe3+. But if we are writing individual steps, this is step number 1, this is step number 2. So here iodide and H2O2-, they are not reacting with each other directly. First Fe3 plus reacting with iodide, and Fe3 plus is now reduced to Fe2 plus, change in oxidation state, and I minus is oxidized to iodine. This is oxidation, this is reduction. In the next step, now this Fe2 plus, it is reacting with H2O2 minus, and this is again oxidized to Fe3 plus, and this one is reduced to sulfate. Okay, now if you add these two equations, basically you will get this equation, because Fe2 plus, that will be cancelled from both sides, and also Fe3 plus. So this is the role of this catalyst. See here, this is the intermediate that is formed, and Fe2 plus is forming from Fe3 plus. So iron can switch between 3 plus and plus 2, so that is why it can act as catalyst. Okay, variable oxidation state. Second reason, large surface area. Transition metals, we can get them in finely divided state, that is powder form, or their compounds are also possible to get in that particular physical state. Now more fine is the character, that is if the particles are very fine in nature, powder form like this, obviously surface area will increase. Now when surface area is increased, as the reactions are occurring on the surface of metals, now adsorption of reaction, that is a substrate absorption will be very good, and as a result these adsorbed reactant or substrate, they can react faster. So higher is the surface area, higher will be the reaction rate, and they can come close to each other also. So large surface area, this is another reason for which they can show catalytic property. Examples of some catalytic properties. Now we will see. The first example, conversion of sulfur dioxide to sulfur trioxide. Here the catalyst that is used, either platinum or vanadium pentoxide, and the process is known as contact process. By this process, SO2 is oxidized to SO3. So first V2O5 is reacting with SO2 and it is converted to SO3, and V2O5 is changed to V2O4. Now V2O4 is again reacting with oxygen. Basically this reaction in presence of air, if we are doing, oxygen will be available, and V2O4 again oxidized to V2O5. So in V2O5 oxidation state of vanadium is +5, but here the oxidation state is +4. And how we will understand it? It is very easy to understand, because when it is 4 oxygen, that means each oxygen -2, total negative charge -8. So total positive charge must be +8, but 2 vanadium atoms are there, so it is +8 divided by 2, that is +4. So in this way you can understand the oxidation state. But the point is V2O5 is changing its oxidation state. It is forming the intermediate V2O4, which is having another oxidation state, and again it is going back to its original oxidation state. Okay. Next example we have already discussed in the last slide. Now come to the third one. Here cobalt salt is used as catalyst, any cobalt 2 plus salt. And what is the reaction? It is decomposition of bleaching powder. Now bleaching powder, there is presence of OCl minus ion. In the first step, cobalt 2 plus is converted to 3 plus, and these two ions are formed. Now 3 plus is reacting with HO minus, again it is reduced to 2 plus and water oxygen. So here from OCl minus, ultimately this, if you add this to equation, hydroxide ion will be cancelled. So this will be as the final product. Fourth example, copper chloride. It is used in Deacon's process for the synthesis of chlorine gas. And for source of chlorine, we use HCl and we oxidize it with atmospheric oxygen. But the catalyst that is used is copper chloride. Some more examples. TiCl3 titanium chloride, it is used as Ziegler-Natta catalyst, which is basically the polymerization of one alkene. Now one alkene is basically terminal alkene. That is terminal position, there will be double bond. So general structure if we write, it will be like this, CH2 double bond, then there is any R2. But see, this is one alkene, 1, 2, and then 3, 4, 5. but the position of double bond is 1. So that is, it is 1 alkene. So if there is polymerization of this CC double bond, then this catalyst is used. It is known as Ziegler-Natta polymerization. PDCl2 is used for Waker process, and Waker process is basically synthesis of ethanol. Ethanol means, L means what? Aldehyde. So 2 carbon, because it is eth. So CH3 CHO, ethanol. And this is the product, and you are getting it from ethene. Ethene is CH2 double bond CH2. So this is actually oxidation. And in this oxidation, PDCl2 is used as catalyst, and the name of the reaction is Waker process. Then nickel, palladium, platinum, they are used as catalysts in hydrogenation reaction, which is very common reaction in organic chemistry. If there is any CC double bond or triple bond, then hydrogen gas is used in presence of these metals, and hydrogenation reaction, that is addition of hydrogen occurs, and unsaturated compounds are converted to saturated compounds. Next example, MnO2. It is used as catalyst for the decomposition of hydrogen peroxide. Platinum or rhodium, they are used in Oswald process, which is basically the manufacturing process of nitric acid. Okay, so these are the examples. Now, based on these examples, see this problem. Here we have 4 catalysts in column, first column, and the processes in the second column. So you have to match it. That is, which catalyst used in which one. PDCl2, it is Waker process. We have just discussed. TiCl3, Ziegler-Natta. So B is 1, A is 2. A is 2, B is 1, that you can find in this option. Okay, so see, just solving 2, you can easily understand which option will be the correct option. CuCl2, that is used in Decon's process. So C is related to 4 and D is 3. D3C4. Okay. So it is simply memory based question. If we want to answer it, we have to remember this. Which one of the following characteristic of the transition metals is associated with their catalytic activity? 4 statements are given. Basically, you have to find out which is the actual reason for which they show catalytic activity. And it is very clear, it is the variable oxidation state for which it shows catalytic property. We also have some other reasons. High enthalpy of atomization. Now, high enthalpy of atomization, that is actually associated with number of unpaired electrons that are participating in metallic bond. Remember, enthalpy of atomization we have already discussed in first or second class, because when we have discussed the physical properties, that is how the melting point and boiling points are changing, because that is directly related to metallic bonding. And metallic bonding is related to enthalpy of atomization, but it has nothing to do with catalytic activity. So this is not correct option. Then paramagnetic behavior. Now paramagnetic behavior is associated with unpaired electron. Higher is the unpaired electron number, higher will be the paramagnetic property. Again, nothing to do with catalytic activity. And the last one, color of hydrated ions. Last class we have seen that because of presence of different d electrons, dd transitions possible, and if the corresponding energy falls in the visible region, we can see color. But for D0 and D10 metal system, color formation not possible because DD transition is not possible. So here correct option will be the first option. Any doubt? Next property, formation of interstitial compound. This type of compound formation we have not seen in case of S or P2. So these compounds will be formed when very small atoms such as hydrogen, nitrogen, carbon, they are getting trapped inside the crystal lattice of metals. Okay. Now transition metals can form a number of these type of compounds in which they take atoms of very small size in the vacant space that is available in the lattice. So here we have a picture for this. These are the interstitial voids where some small atoms can be trapped, and as a result there is change in the ratio of the compound. So suppose you have any iron oxide and there is presence of some trapped atoms. Now the ratio of iron and oxygen, that will also change. These are some of the examples. It is mostly due to variable valency of transition metals. Sometimes non-stoichiometry is caused by defects in solid structure. So these trapped atoms, that is also one type of defect. And see, normally what should be the formula for iron oxide? It is either FeO or Fe2O3. But here the formula is different, and it is because of these trapped atoms. Now the stoichiometry is not maintained. It is non-stoichiometry. Okay. They are typically neither typically ionic nor covalent, and also they are non-stoichiometry. So you cannot say clearly whether it is completely ionic or covalent. That's not possible to predict. As a result of filling up this interstitial space, now they become rigid and hard compared to the situation when there is vacant space available. And that has to be. These interstitial compounds, they are having similar chemical property, but as the parent matter. That means when there is no trapped atoms and when there is trapped atoms, if you compare the chemical properties in these two situations, they are almost same, but if it is physical property, now there will be huge change, especially density, because see, volume is fixed, but mass is changing because some extra atoms are now inserted. So obviously density will increase. Hardness will also increase because now rigidity is high. Conductivity will also be, there will be change because when there is vacant space, electrons from the metals, they can move very freely. But when there are some vacant space no longer available, these electrons from metals, they cannot move very freely. So that is why all these factors are affected, which are basically physical properties. For example, steel and cast iron, they are hard because, why it is hard? Because there is some trapped carbon atoms present. Okay, so this is the example. Next property, alloy formation. Alloy formation possible. It may be mixture of two metals or one metal, one non-metal. So iron when mixed with carbon, there is formation of steel. Copper, tin, both are metal. This is metal, this is carbon is non-metal, right? But the next example, both are metals and it is forming bronze. So what are alloys? Alloys are basically as if solid solution, because you are mixing two solid, and normally when we say solution, the first picture comes in our mind that some solid is dissolved in liquid, but that doesn't mean that you cannot have solid solution. Solid solution is also one type of solution, but two solids are there, so one solid will be present in large amount, another solid will be in lower amount. So the large amount, that will be considered as solvent, and the solid which is present in lower amount, that will be considered as solid. So they are homogeneous solid solution obtained by melting the component. So if you are taking copper and tin, you are melting it and then cooling it, and you are getting the alloy bronze. These are formed by metals whose atomic radii differ by not more than 15%. So what is it? It means, suppose copper and tin you have mixed, you are getting bronze. Now the size of these two metals, that is the condition for forming alloy, is that their size should not be differing more than 15%. If it is that, then this type of solid solution formation not possible. So if it is within 15%, atoms of one metal can easily take up the position in the crystal lattice of the other. So that is why sizes should be close, not there is much large variation. That is not, if present, that will not be helping to form alloy. Now transition metals, their atomic radii, though it is decreasing from left hand side to right hand side, but still the difference is not very drastic. They are almost close to each other. So that is why similar atomic radii as present, they can form alloy. Alloys are generally harder, higher melting point, more resistant to corrosion compared to individual metal. So here you have obtained bronze. So compared to individual copper and tin as metals, which are the components, now it is more hard, melting point high, resistant to corrosion. And that are actually the reasons for which we make alloy. What is the purpose of making alloy? The purpose is to make it more durable so that we can apply all these alloys in our day-to-day life and they can have some industrial application. Okay. Most commonly used are ferrous alloys. That means keeping iron fixed. There may be different types of metals that you can mix with it and you can get different types of alloys. So keeping iron same, you can mix chromium, vanadium, molybdenum, tungsten, manganese, etc. So here we have some of the examples. So all are steel because iron is fixed, but depending on what the other component, there may be different name. So when you are mixing chromium 10 to 20%, that is main part is iron and some amount of chromium is mixed, it will be called stainless steel. Then you are mixing 3.5% nickel to iron, you are getting nickel steel. Another nickel steel is there, but name is different, and here nickel amount is comparatively high. Okay, though the same component, both are nickel and iron, but depending on this ratio also, alloy is different. Then vanadium steel, tungsten steel, manganese steel, molybdenum. So these are very easy to understand because from the name you can understand which metal is actually added. Okay, so these are the examples of alloy steel. Any doubt? Next topic, oxides, oxoanions. Oxide means metal oxide and oxoanion means some negative charge will be present. It may be oxocation also. In that case, some positive charge will be present. Generally, transition metal oxides are formed by the reaction of transition metals with molecular oxygen at high temperature. Except the first member of 3D series, which is scandium, all other transition metal elements, they can form ionic metal oxide. Here we have the general formulas. See, MO, that is ratio is 1:1, then M2O3 ratio 2:3, M3O4, MO2, MO3. So different types are there. Now why there are different types? Because metals can show, these elements, they can show variable oxidation state. So see, here oxidation state is +2. Next one oxidation state is +3. Then oxidation state is +4. So in this way, not +4, sorry, M3O4, that means total negative charge is -8. Total positive charge must be +8. 3 metals, that means oxidation state is 8/3. Then MO2 oxidation state +4. This is +6. So variable oxidation state as possible. So that is why different formulas for oxides. As the oxidation number of metal increases, ionic character decreases. So that is why Mn2O7, which is having oxidation state +7, which is the maximum oxidation state possible for Mn. But suppose you have another manganese oxide, which is MnO2, oxidation state +4. Now both are manganese oxide. But what is the difference? Oxidation state is +7 in the first one, +4 in the second one. So which one will be more ionic? MnO2 will be more ionic. So higher is the oxidation state, then ionic character will decrease, covalent character will increase. Oxides are generally basic in nature because we know when it is metallic oxide, because D block elements are metals, then it is mostly basic oxide. If it is non-metallic oxide, it is acidic oxide. And if both the properties are present, non-metal, metal, then it will be treated as amphoteric. But in this case, as they are having mainly metallic nature, so they are generally basic, but you can also find some amphoteric or basic character, acidic character. And when you will find it? When oxidation state is very high. Because when oxidation state is very high and it is forming oxide, then it is very electron deficient state. Just take this example, Mn2O7. It is metal oxide, that is fine. But still it will have acidic in nature. Why? Because oxidation state is very high. It is electron deficient. So it will be having acidic property. So it is basic when the metals are in lower oxidation state, but acidic when they are in higher oxidation state. So same metal, that is when it is forming two types of oxide, one oxide is having more higher oxidation state, that will be acidic in nature. So here we have some examples. Scandium, it can form only one type, and here oxidation state is +3. This is not ionic as it is mentioned here. Then titanium, see, three different types. This is +2 oxidation state, this is +3, this is +4. So when oxidation state lower, +2, +3, these are basic. When it is moving towards high, gradually it will be amphoteric first, then it will be acidic. Then for vanadium, VO is having oxidation state +2, it is basic. +3, this is also basic. Now it is +4, this is +5, and they are gradually becoming amphoteric and then acidic. Chromium also +2. Okay, it is +2, this is +3, then +4 and +6. So as it is moving towards higher oxidation state, gradually it is becoming acidic in nature. Then manganese, lower oxidation state, they are basic. This is intermediate state, amphoteric. This is also amphoteric, but this is acidic. Iron, basic, amphoteric, basic. Here we do not have any acidic. Fe3O4 is basically mixed oxide. It is combination of FeO and Fe2O3. Then basic, +2, +2. This is +1, but this is +2. And this is +2. Okay. So these are the examples. Any doubt? So see here oxidation state of metal. Starting, you can see all the examples. Starting from +2 up to +7. All examples are present here. Any doubt? So this is also some 2 or more slides are there that are related to oxides and oxoanions, but it will take time. So I will like to finish it here. So regarding all the slides in today's class, if you have any doubt, please mention. So we are ending the session here as there is no doubt. Thank you for listening.